All right, in section 3.4.2, I want to solve homogeneous second order linear differential equations. All right, quite a mouthful. So in this section, we'll be solving homogeneous second order linear differential equation in a single function y of t. More precisely, we'll learn how to solve a differential equation, which is y double prime plus by prime plus cy equals 0, where b and c are real numbers. All right, so let me spell this out. Homogeneous means the other side is 0. Second order means the biggest derivative is 2. Linear means the coefficients are just constant. And then differential because it involves derivatives. All right, consider the differential equation, y double prime minus 7y plus 12y equals 0. So we'll learn the method to solve any of those using this specific example. So the first thing you should do is you rewrite the differential equation as a linear system of differential equations. So the type that we just learned how to solve. So I'm going to use y1 equals y and y2 equals y prime. So this is quite clever because my original system right here depended on multiple variables and only involved the first derivative. So I'm going to use these two as two different functions, and then I'm going to be able to rewrite it using only the first derivative. Let's see how. All right, so y1, I want to know something about y1 prime. That's going to be, well, y1 is y, and so that's going to be just y prime, and y prime, well, is y2, so that's 0 y1 plus y2. And then the second derivative, so y2 prime, that's y prime prime, that's y double prime. I also need to write that in terms of y1 and y2, and so I'm going to use this differential equation. If I isolate y double prime here, I'm going to get 7y prime minus 12y, and so I guess 7y prime minus 12y, and if I write this in terms of y1 and y2, I need minus 12y1 and I need 7y2. And so what I get is y1, y2 prime is 0, 1, 7 minus 12, no, minus 12, 7, sorry, times y1, y2. All right, so this is the type of system we know how to solve. So solve the linear system of A using diagonalization. All right, so my matrix is 0, 1, minus 12, 7. I need to diagonalize it. Let's find its eigenvalues. So minus x, 1, minus 12, 7 minus x. I get x squared minus 7x plus 12. That's going to be x minus 3, x minus 4. So I have two eigenvalues. I have 3. Let's find its eigenvectors. So I have minus 3, 1, minus 12, 4. When I reduce this, I get 1 minus a third, 0, 0. And so for s here, I'm going to get xy. X will be a third s. Y will be s. And so I can take my first vector to be, I'm going to take s equals 3. So I get 1, 3. All right, a lambda equals 4. That's going to give me minus 4, 1, minus 12, 3. If I reduce this, I'll get 1 minus a fourth, 0, 0. And so xy, this is my free variable right here. So xy, x will be a fourth of s, and s. I'm going to take s equals 4, and I'll get 1, 4. All right, so that means my matrix is 1, 3, 1, 4, and the diagonal matrix will be 3004. All right, so I need to solve for u. U equals 3004 times u1, u2, u prime. And so I'm going to use u1 equals c1 e to the 3t, and I'm going to get u2 equals c2 e to the 4t. And then y is going to be pu. So that's 1314 times c1 e to the 3t plus, c2 e to the 4t, and then I'm going to multiply them. I get c1 e to the 3t plus c2 e to the 4t, 3c1 e to the 3t plus 4c2 e to the 4t. All right, so that's the solution for y. Bit complicated, but we got through it. But that's not the one we cared about. We don't care about y1, y2. We only care about y. And so I'm only going to keep y1. So find the general solution for c. Y is y1, and so it's c1 e to the 3t plus c2 e to the 4t. All right, so let's check that this is indeed a solution for the differential equation. So I want to check that, what was it, y double prime minus 7y prime plus 12, I think. Let's double check. Right here, minus 7 plus 12. Good. All right, so y prime is 3c1 e to the 3t plus 4c2 e to the 4t, and y double prime is 9c1 e to the 3t plus 16c2 e to the 4t. So if I plug all of that in, I'm going to get 9c1 e to the 3t plus 16c2 e to the 4t. Then I'm going to subtract 7 times the first one, so minus 21c1 e to the 3t plus 7, so 28 c1. Oh, sorry, there's a y missing here. c1, what do I have? 28 c2 e to the 4t, and then I want to add 12, so plus 12 c1 e to the 3t plus 12 c2 e to the 4t. All right, so what will I get? I get 9 minus 21 plus 12 c1 e to the 3t, and then for c2 I get 16 minus 28 plus 12, I get 0 as well. And it works. All right, so here's the method to solve a quadratic linear equation. Y double prime plus y, by prime plus cy equals 0. So first you take y1 equals y and y2 equals y prime. You rewrite the differential equation as a linear system of differential equations. So y1 prime, that's y prime, so that's equal to 0, y1 plus y2. So that one will always be the same. Now the second one depends on the actual equation, so that's y double prime, and then you solve for y double prime here. So in this case, that will be minus by prime minus cy, and so we get minus cy1 minus by2. All right, so you solve for y1, y2 using diagonalization, and the answer is whatever y1 gives you. All right, so we saw it for degree 2. It would actually work for a higher degree as well. You would just need more and more variable. So here's an example. The last method would work for differential equation of higher order. For something of order 3 like this, that would involve the third derivative, you would take 3 different variables and you would build it just the same way. So here, y1 prime would be y2, y2 prime would be y3, and for y3 prime, that's y33, and you rewrite it using the original DE, the original differential equation.